I will, Xabier, stand with an interpretation of the result. And let me just have 1 second to explain the details for the plan for tonight. I'm going to give you a tapas card that basically means a way to try the typical Spanish tapas for free. But you need me to tell you in which bars it works. So the idea is that I can meet you in the hall of the hotel at 9 or at 9:30. Well, so what time do you prefer? 9, 9:30? 9 is okay? Yeah. Okay.
So basically the idea is we can go as a big crowd from the entrance of the hotel, we can all explore the bars with you as a guide, and then get a bit lost, but not too much. Okay.
Okay, so as Manuel said, we performed this work between me, Manuel, Xabier, and Santos. As well, we did the work thanks to the support of the Robotic network, which provided funds for an stay of Manuel and me in San Sebastian for a month. And the objective is to build a theoretical model, a theoretical minimal model, to explore the effects of sensorimotor spatial coupling in oscillatory models. We're starting seeing how dynamics models in cognitive science were being increasingly successful. And we saw that these models provided 2 central contributions to the explanations and models in cognitive science that mainly were that first, cognitive mechanisms could be better understood in terms of dynamical systems instead of symbolical computation. And the second one is that cognitive behavior could emerge out of recurrent sensorimotor loops in a self-organized way. So the first claim is widely accepted in neuroscience, and we see how some of the latest progress on both mechanistic or dynamic behavioral levels of dynamical modeling is related to dynamics and often to oscillatory dynamics. Sorry. Okay. However, the second claim, the claim of behavior emerging out of sensorimotor loops, is not that often used. And we can see a lot of examples in neuroscience where experiments are performed in subjects which are lying passively receiving a stimulus, or even anesthetized animals or pieces of cortex which are extracted in a culture and just stimulated with a punctual input and see how they respond. So we wanted to explore how the effects of being situated in a world, continuously interacting with it, affects the dynamics of an oscillatory controller. And for that, following the spirit that Randy explaining of minimal cognition, minimal models, for trying to explain more complex phenomena, we took the HKB model, which is a minimal model of coordination dynamics. And this is a model that represents the coupling of 2 connected oscillators. And this is a paradigmatic model of coordination in oscillatory systems in cognitive science. And we choose it as well because its dynamical properties are well studied, and they are mostly defined by its phase space, which we can see here. It has three different modes of functioning. And as you see this, okay, we have these 2 oscillators here, and we have the phase of each one, and all the system is described just by using the relative phase between the 2 oscillators with this equation here, where delta omega is the difference in the natural frequencies of each oscillator, and A and B are just coupling parameters. So we have these 3 modes of behavior, where the red ones is a bistable behavior, where the both oscillators can synchronize in an in-phase mode, where both oscillators are oscillating at the same time, or in an anti-phase manner, where they are alternating. As well, we have this parameter, delta omega, the difference of the natural frequencies, which acts as a control parameter of the system. And as we increase the value, the frequency difference of the oscillators, we move to this blue mode of behavior, which is a monostable system, which can only synchronize in an in-phase manner. As well, if we increase further the value of delta omega, we reach a metastable mode, which is this green zone here, represented by this picture, where all the attractors disappear, and we have what is called a metastable coupling, where there is no attractor, but there is this point, which is like the shadow of an attractor, in which the system stays much more time than in all the other parts of the system. So the system is going to be all the time coming back to this point and staying us for some time and going back. Anyway, for the model we're presenting, all the behavior of the system is always in this monostable system, monostable part, where we only have in-phase synchronization. This model has been used for a lot of examples. I'm sure most of you know them. The most basic one is finger synchronization. You can try to synchronize your finger and you can synchronize them in phase like this or in anti-phase like this. So you have a bistable system. But if you try to synchronize them faster, you're going to see how there is only one way you can synchronize them. If you try to synchronize them like this, you are going to end up doing this because it's impossible for us to do it if we move too fast. This model has been used in a lot of examples. One of is production of the speech, and we can use the HKB for modeling the coordination of different parts of the tongue and the lips as well. This is why we were also interested in this model, is that it has been used for modeling coordination between brain areas, from coordination between neurons to coordination between larger parts of cortex or brain areas, or even coordination between different brains. However, in all these pictures, we cannot analyze the sensorimotor loop as a specific part of the system. We either have a system where we have these cases where there is coordination between parts of the brain, but we do not take into account any coordination of the subject which have these neurons coordinating. Or we have situations like this, two subjects coordinating, but the HKB model models the whole dynamical system. And we cannot tell what is the subject and what is the environment or how they coordinate. So what we did is to create a new model where the HKB is a coordination between two parts of a neural controller of a robotic agent. You can imagine one oscillator representing a neural sensory cortex, which is receiving a stimulus, and the other one representing a motor cortex, which is moving the wheels of the robot. So we are going to see how this HKB system behaves when it is part of a larger system in which there is an ongoing sensorimotor coordination. And the question we were asking ourselves is, what does situated coupling bring in this model? So for that, we are going to create, to analyze three different models to analyze what comes from being situated in a world where we are continuously interacting and with a closed sensorimotor loop. So the first one is the situated-HKB I just talked about, which is interacting with a world, performing a task, and in this case we have a world of a sensory gradient, and the task is to climb the gradient and reach the center of the gradient. The second model we have is a decoupled HKB, and this is just an HKB system with no input or constant input, and it is not interacting in any way with any environment. And the third one is a passively coupled HKB, where we have an HKB as the decoupled one, but we provide the HKB an input which has been recorded from a situated HKB in order to analyze a system that is receiving the same input as if it were coupled in a real sensorimotor interaction. So we first start with the analysis of the situated-HKB, in which we have this HKB in a robotic body interacting with a gradient world performing this gradient planing. Okay, we describe the system with, we can describe the position of the robot with respect to the center of the gradient with two variables, the distance from the center of the robot to the center of the gradient, and the angle of the orientation of the robot with respect to the center of the gradient. As well, we're going to provide the again an input, which is going to be the intensity of the stimulus of the gradient, which we are going to call eta, which is linearly dependent to the distance to the center of the gradient. So the intensity increases as we move towards the gradient. And finally, we're going to describe the activity of the motors, but with the phi, which is the phase difference between the two oscillators, which behaves according to this HKB equation. Okay, and we can simplify all these variables and then end up with just three differential equations that describe the dynamics of the whole system. We have phi, the phase difference between the two oscillators, which is the HKB adding an input, which is going to depend on the derivative of this stimulus of the gradient. We're going to have eta, which is the stimulus, and we're going to have alpha, which is the orientation. We can eliminate d because it's linearly dependent with the value of eta. Sorry. Okay, now we can see that we have some free parameters. We have S, which is the sensibility of the sensor. We have A and B, the coupling factors, and we have C, which is a parameter that breaks the symmetry between the two motors. Okay, and as we have just these three variables, we can adjust them just by trial and error, hand tuning, and we find three parameters describing the values of C, A, and B. And we let S as a free parameter to try to find different behaviors, because A and B and C are chosen so that the AM performs a gradient climbing behavior, and we try to see what happens if we modulate the value of S. Okay, so we try different values of S from 0 to 15, and we see a lot of different types of behavior. When S is too small, we have this cycloidal behavior where the agents continuously turns over itself and finally reach the center of the gradient. As we increase S, we find more effective strategies where the agent goes directly to the center of the gradient. And if we have a really large value of S, we have an agent that starts doing this spiral movement, doing this detour while reaching the center of the gradient. So we have what seems to be qualitatively different behaviors, and to understand better what's going on, we have performed a dynamical analysis of the system, where we have linearized the dynamical system, these three differential equations around its fixed points, which are going to be an attractor and a repeller for all the possible values of S. And with this linearization, we can get the eigenvalues of the system that are going to tell us what kind of attractor we have and what's its intensity or the force of attractor or the repulsion in the case of a repeller. So if we have the eigenvalues are negative, we are going to have an attractor, and if the eigenvalues, the real part of the eigenvalues is positive, we are going to have a repeller. As well, if the eigenvalues are real, we are going to have a node attractor or repeller, which is going to have this shape. And if the eigenvalues are complex, we are going to have a spiral. And the attraction or repulsion is going to oscillate in this way. We can easily find the eigenvalues of the system for each value of S. And as we have three differential equations, we are going to have three eigenvalues. And these eigenvalues are going to describe the attraction and the repulsion in the attractor and repeller. And as well, we can see that we have some part. The solid line is the real part of the eigenvalue, and the dashed line is the imaginary part. So we can see also we have some parts of the system where we have imaginary parts. So we are going to have these spirals in the attractor and repeller. And we're going to have some parts where we don't have an imaginary part, so we have a node attractor, not in the case of the repeller. What we want to do here is to see if there is a correlation between the solution of the dynamical system and the behavior we were observing previously. So for the first region, for the first region here, where we have an imaginary part in the attractor as well as the repeller, we have a spiral repeller and spiral attractor, and we have this cycloidal movement of the agent. And we see here that the imaginary part starts decreasing until it disappears, and this was after. Okay, first we have this transition point here in 2.4, where the imaginary part of this repeller, of this agent value disappears, and here changes also, and it's very small, but there is also a abrupt change in the value of the real part. So we have a point where the configuration of the agent values abruptly changes. So what does it mean? It means that we have a transition between this kind of behavior to this behavior where the agent stops this cycloidal movement and goes directly towards the source of the gradient. And this is as well, this point of transition is the point of critical coupling, where we have this better behavior, the point where the agent goes fastest towards the gradient source. As well, we have other two transition points in here and here, where we also see changes in the behavior. We see that the agent changes from entering this final circular trajectory from within to entering from the outside. And in here, 10.4, where we have this, we have first this change of a spiral becoming a node, and then the node becoming a spiral in a different plane. And we have this slight more subtle transition of the agent orienting itself at the beginning of the movement like this, or doing it oscillating a bit. So we have these qualitatively different behaviors which are coincide with different dynamical descriptions of the system. So in order to get back to the question we were having before, what's the role of sensorimotor coordination in all this, in these dynamical changes of the system correlated with behavioral changes? And the question we want to ask ourselves is if we can, just by knowing the neural controller, the properties of the HKB system, could we explain something about these behavioral transitions? Okay, so for that, we create a new model, which is the decoupled HKB, which is the HKB system with no input, and its properties are well known, and we find one agent value for the attractor and the repeller. And what does it mean? If we analyze the attractor and the repulsion of the system, we find that whereas in the situated-HKB we have a complex behavior which unfolds in different dimensions and different time scales, in the decoupled HKB we have a really simple behavior which has this exponential attraction or repulsion in the case of the repeller. So there is a lot of things about how this attraction works in different time scales that cannot be explained by just knowing what's the dynamics of the HKB alone. Okay, but this comparison is somehow unfair. It's trivial that the HKB alone is going to be different than the situated-HKB. So, because we have on one side a one equation system and on the other side a three differential equation system. So, the systems are going to be much more complex with three equations. But we can ask ourselves if the difference between the decoupled HKB and the situated-HKB lies on the fact that the situated-HKB is receiving a complex input generated by the history of interaction. Okay? So we ask ourselves if the dynamical structure of the situated-HKB could be explained just by knowing what's the structure of this input that it's receiving. So for that we designed a new model which would have been called passively coupled HKB, in which we have an HKB that receives an structural input generated by a situated model. So we simulate an situated HKB model, reaching the radio source, we record the input the HKB model has received, and we put this input to the passively coupled HKB. So, in order to ask this question, if the different modes of behavior could be explained by this particular structure of the input. So we describe the system just by adding a new equation, which is the same than this phi here, that is a phi star, which receives exactly the same input than the situated-HKB. As well, if we solve the system, we find that the eigenvalues of the situated-HKB, of the passively coupled HKB, will be a combination of the eigenvalues of the situated and the coupled HKB. As we can see here, we have these 4 eigenvalues, a combination of situated and the coupled. And and for knowing what's the part of the situated-HKB eigenvalues and the coupled HKB eigenvalues in the passively coupled HKB, we can describe the behavior of the system around the fixed points as a set of exponential functions. And we find that the term lambda 4, which is the 4th eigenvalue here of the decoupled HKB, is only present in the phi star, which is the variable for the passively coupled HKB. Moreover, we find that these 3 first values are exactly the same in phi and phi star, in the situated and the passively coupled HKB. Meaning that we can describe the dynamics or the behavior of phi star just knowing the dynamics of phi and adding an extra term that we are going to call delta phi star. And this extra term is described with an exponential with the 4th eigenvalue and an amplitude term, a sub lambda 4, which is going to be defined by the initial difference in the values of phi star and phi. Okay, what does it mean? We can think the system as being in the attractor, for example, where the values of phi and phi star is going to be the same, and we can think that at some point the system has a perturbation. Okay, it has a perturbation in value of phi star. So it's going to be a difference between phi star and phi, and the system is going to compensate this difference with this exponential form. Okay, so at this point, in response to this perturbation, the values of phi star and phi are going to be different for some moments of time. Okay, but this is not a big deal. But if we think as in real-world system or biological systems as continuously having been facing perturbations all the time, this is not just going to be a punctual thing, but it's going to be present in all the behavior of the system. So if we have all these perturbations, a series of perturbations that are responded with these exponential forms, the difference between phi and phi star is going to be computed by integrating all the exponential functions multiplied by the amplitude of the difference fluctuations. Okay, so we have developed this theoretical result, and we have proved it with simulations, and what we have done is we have introduced a perturbation in the values of the situated-HKB and measure how big is the perturbation, the resulting fluctuation, in the values of the passively coupled HKB or phi star. And we find that if we introduce a white noise like this gray signal in here, the fluctuations present in the passively coupled HKB are much bigger and have a structure of its own, have correlations that were not present in the initial fluctuation. Here's the first cue about how different is going to be the behavior of the passively coupled HKB compared to a system which is continuously interacting with the world. For quantifying better how sensorimotor interaction modifies or shapes the dynamics of the system, we have performed a different measure that we have called the dynamical signature of the HKB, trying to see how the coupling shapes the dynamical landscape of the system, to really see how different is the system which is coupled interacting with the world with the system that is just receiving an input in a passive manner. So this dynamical signature is like a density distribution of the neural activity. We measure the density of the derivative of phi related to phi in the situated-HKB and the phi star in the passively coupled HKB. So this dynamical signature will be specific of the task the agent is performing. It will be something like a dynamical functional brain correlate of the gradient climbing task the agent is performing. So we try different values of S, and we see how in the situated-HKB this dynamical signature has a pattern which is going to be specific of the behavior of the agent. And this phase space is going to be shaped with this particular form. Whereas in the passively coupled HKB, we don't have the shape at all. We just have this form, which is the initial form of the HKB phase space with this blurring, which is a product of the noise we introduce to compute, to explore the phase space. Because what we do is to compute this density distribution by resetting the system its amount of time with random values and see how much percentage of the time the system is in one point or another. So as an effect of this resetting, where the system starts in different points, we have this blurring of the form. As well, we can see how different behaviors have different shapes, different shaping of this dynamical landscape that we are trying to capture with this dynamical signature, and as well the passively coupled. But the passively coupled HKB never retains this shape of that is created by sensorimotor interaction. So for recapitulate the results, the first one is that the situated-HKB model presents transitions of behavior that are between transitions between qualitative different types of sensorimotor behavior. And these transitions cannot be deduced from the behavior of the decoupled or passively coupled HKB models alone. Instead, this transition of qualitative model behaviors emerge out of particular sensorimotor modes of interaction. And we need to analyze this whole body-brain environment system to understand what's going on. We cannot just have the passive system analyzed for understanding them. As well, we saw how transient trajectories in the situated-HKB are far from trivial and holding a different time scales, whereas transient trajectories in the coupled HKB are much simpler. The third result is that the passively coupled system receiving an input generated by a situated-HKB suffers correlated and greatly amplified fluctuations that are not present in the situated gradient. And the last result is that the dynamical signature can show us how the coupling, the sensorimotor coupling, dramatically changes the phase space of the HKB system. And we cannot see this shaping when the sensorimotor loop is broken, in the case of the passive HKB. So, as conclusion, what is crucial is the fact that under situated conditions, the dynamic of the HKB can be modulated by precise and interactive structural coordination between its internal dynamics and the sensorimotor environment. So we have these two levels of coordination, which is the internal coordination of the HKB and the sensorimotor interaction, which are coupled together and explain the behavior of the system. And we cannot break any of these loops because we are not going to understand how the system is behaving. Okay. That's all. Thanks for your attention.
Questions? No? Well,
maybe it's just quite too late. I feel bad for torturing people. But it's just 4 slides, so I guess it makes a bit sense. I was proud of this, and also I wanted to explain a little bit of the motivation and what kind of problems could this type of model solve. So this is the model introduction and a little bit of comparison between what is lost when we study a system as isolated. In fact, it was a bit surprising for us that the